those of you who had a chance to go back and just go through whatever we have discussed in the last class, you will remember that we were discussing about a special type, a special family of MOSFETs. Those are called enhancement type MOSFETs, where to begin with there was no channel, and we saw that how a channel got enhanced, and we also studied the output characteristics of that particular device in the last class. Okay. So today we will begin from exactly from that point where we stopped. That is the output characteristics of the enhancement type MOSFET. We worked out this entire example using n-channel system, but you could realize that how our batteries will change their polarities, but the phenomena will remain same if I consider a p-channel enhancement type MOSFETs. So let us begin. Okay, so I guess you can see my screen.
Yes, ma'am.
Okay, so let us start from the same point where we left off, that is the output characteristics of enhancement MOSFETs. And here the most interesting part that we saw was that how there was no channel, and you
Ma'am, you're not audible. Hello, ma'am.
Hello.
Hello.
Yes,
Hello.
ma'am.
Yes, ma'am.
Yeah. Sorry. There was a sudden power cut. So let us start our discussions again. So we were talking about the output characteristics of this enhancement MOSFET, and I asked you to try to draw the transfer characteristics of this device um, using the output characteristics. I hope you tried. Have you tried to see that how the transfer characteristics might look like? So here was the output characteristics, right? And we already know that how from JFET that how to extend the knowledge that we have from the output characteristics and transfer it in terms of transfer characteristics, where the y-axis will be ID and the x-axis will be VGS. So here, if we two important things that we had in this curve was, first one was this changing slopes, okay? So that we have to take into account, and we know that as we saw that increasing VGS means increase that resistance will decrease, right? And resistance will decrease means that slope of this curve should increase. So increasing VGS should increase the curves like this. And if you extend it backwards, then the transfer characteristics that we have look something like this. Okay. So the most important part to see here is that the transfer characteristics for this device is going to be in the first quadrant. Okay, so in case of n-channel JFET, we saw that as VGS were negative and ID was positive, so we found the curve transfer characteristics lying in the second quadrant. If you remember, we had a curve like this. Okay, so we had a curve that was lying in the second quadrant, and it was something like this. Okay, like this. So in case of this device, instead of having a curve like this in the second quadrant, what we have here is in first quadrant. Why? Because VGS in our cases here, if you just go back and see, then the G terminal was in positive potential, VGS was positive. So this curve is going to lie in the first quadrant. That is the first difference that we have. The second thing that we have to keep in mind is there was a voltage called V threshold. We defined it in the last class, right? V threshold was the voltage, minimum voltage required for enhancing the channel, the beginning of enhancing of the channel, the inversion. For that, you needed a certain amount of voltage present, okay? Until that, there was no channel. So until that voltage reaches in VG, we don't have any current. Okay. Then the current starts growing. So we extend these curves backward, and we have a curve like this that grows, and it touches the x-axis at V threshold. So if you found a curve something like this blue curve that I'm showing here, then your transfer characteristics was right. Okay. If you found something else, then try to correct whatever we did, because the curve that we are looking for should look something like this. Okay, so this is the transfer characteristics of that device, n-channel enhancement type MOSFET. So now let us move on and talk about the other half that we left off, that is the depletion type MOSFET. Okay, so to begin with, I told you that enhancement type MOSFET, when a device which was normally switched off, and depletion type MOSFET was just working, the working principle was just opposite. So that device is supposed to be normally switched on. Okay, so we saw that in enhancement type MOSFET there was no channel to begin with. That means if you don't apply a proper biasing, no current can flow through. By switched off, I mean this, that no current can flow unless you apply a proper biasing. Similarly, in case of the other depletion type, there we already have a channel that is quite similar like JFET. This basically you can connect the principles of enhancement type MOSFET as well as JFET together to get the operating of depletion type MOSFET, which is a normally switched on device. There is a channel, and we squeeze that channel using VGS. So let us see how a depletion type MOSFET works. Okay, so in case of depletion type MOSFET, the main construction wise, the main difference is the channel. Rest is basically the same. Okay, so we saw enhancement type MOSFET in the last class. Here also you have a source, a drain, okay, a substrate is shorted with the source, just like the E-type MOSFETs. And here you have the layers of the oxide and then a metal and then a gate terminal coming out. That is my gate, okay? And here I am supposed to apply a certain voltage VGS. We will see it is positive or negative or 0. We will see that. We'll apply that to control this channel width. So this looks quite similar to JFET, right? In JFET also we did something like that. We made the depletion region from both sides to quench the channel. From both sides it squeezed the channel, and the space available for the electrons to move become smaller and smaller, and the channel finally got pinched off. Something similar is going to happen here, but the dynamics is going to be a little bit more richer, where there will be an aspect of enhancement as well. So let us just step by step see that how this device works in depletion type MOSFET. Okay, so construction wise they are different, that you have to remember. Biasing wise what happens, let us discuss that. So by now you are experts of drawing output characteristics, I hope. So we will go through the entire discussion and we'll draw the output characteristics along the same line. We'll go on continuing drawing the output characteristics. So let us start. So the first things that I think that you already are quite familiar with is that which way to connect our VDS battery. Okay, VDS, the drain to source battery, is supposed to be connected in such a way so that the carriers, the majority carriers, move from source to drain. Okay, so majority carriers here we have N. So majority carriers are going to be electrons. Electrons will drive them from source to drain. That means this side, the drain side, has to be positive. So that is the first battery that we attach to our circuit, because we understand that we have to make the majority carriers flow from source to drain. Okay, now step by step we will consider different values of VGS, similarly as we did in previous devices. In case of JFET, in case of E-MOSFET, here also we'll consider 3 different regimes of VGS. Let us start with VGS equal to 0. Okay, so VGS equal to 0 means there is no voltage between gate and source. That means they are short circuited. So I have connected a wire between source and gate to make them short circuited, making VGS equal to 0. Okay, so this is our first scenario, VGS equal to 0. Let us see that how the circuit will perform. So what do you expect? We have a voltage, positive voltage here. I am trying to draw the output characteristics. Just keep that in mind. I am trying to see that how the current in this channel will vary as I change VDS. Okay, so what will be the value of current if VDS equal to 0? What will be the value of current if VDS is equal to 0?
0. No, current
0. Very good. So it will be 0, right? So as soon as you start increasing the voltage, what will happen? More and more majority carriers are supposed to flow, right? Supposed to flow. They are supposed to get attracted, and these majority carriers will start flowing. So the majority carriers start flowing from source to drain, and at the same time, the conventional current flows in the opposite direction. So ID, the conventional current, also starts flowing in the circuit. Okay, so this is how the current flows. But at the same time, something else is also happening. Okay, what is happening here at this? Just focus your attention here. Here I already have a PN junction. Okay, so I have a PN junction lying throughout this time, because I have now a source and a channel and a drain. The entire parts are basically N type. Somewhere we have a little bit higher level of doping, somewhere we have a little bit lower level of doping, but we have a consistent N material lying in this portion, while the rest of the portion, the substrate, is P type. So along this line I basically have a PN junction. Okay, so whenever I have a PN junction, what is supposed to happen there? Formation of a depletion region. Okay, so let us consider the current. Let us keep the current in our head and also consider the depletion region. So both sides of this junction, both sides of this PN junction, I will have a depletion region spreading into the substrate as well as spreading into the channel. Okay, now just look at the biasing that I have that is causing this depletion region increase or decrease. Just apply the same principle that we had in case of JFET. Okay, so here also you can see, just similar to JFET, this drain terminal is basically N type, but that is attached to the positive side of the battery, right? That means it's a reverse bias. So as soon as you change this VDS to higher and higher values, Though the current flow tries to increase, some opposing force also gets developed, because the depletion region gets broader and broader because more and more reverse bias are being applied in this p-n junction. Okay, so this p-type side is substrate and via source that is connected to the same battery that I have connected. Okay, the p-type side is connected to the negative side of the battery, while the n-type side is connected to the positive side of the battery, applying a reverse bias. So as soon as you go on increasing VDS to higher and higher values, this depletion region spreads and gets broadened. Here in the substrate side, there is lots of space, so the depletion region can grow, no problem. But on the other side, where we have the channel, the space is limited. So depletion region grows, and at a certain value of depletion region, this will be sufficiently high at the drain terminal so that the depletion region inside the channel completely pinches off the current flowing path. The channel is closed due to the application of this VDS. So this is the simplest part of the discussion, where we have VGS equal to 0 and only one source, VDS, the one source that we have applied, has controlled and closed the channel by formation of the depletion region. Okay, so this operation looks quite similar to JFET, right? We applied, we drew almost a similar kind of a diagram in case of JFET. There also we considered VGS equal to 0, and we saw that how VDS caused the channel to get closed. So now you understand that at different points in the channel, the voltage is going to be different. That means the channel, the depletion region is also not going to be symmetric, but near the drain, as the biasing is maximum, the channel will be sufficiently squeezed and finally closed, and you will have a pinch off. So what kind of a graph do I expect? You said that at VDS equal to 0, it will be 0. Then it was linearly increasing, right? But at a certain value, the channel gets closed. So I get a graph like this. Okay, so it increases linearly, then it reaches a knee-like portion, and then it saturates. This is the VGS equal to 0 volt graph. In case of JFET, if you remember, we call this graph, this current, the maximum value of current that we got it, we call that IDSS, right? Short circuited, we called it, because gate and source were short circuited at that point. And if you remember, that was the maximum current that could flow in that device, right? VGS equal to 0, corresponding to VGS equal to 0, the saturation current was the maximum current that could flow in the device. So let us see what happens here. In case of depletion MOSFET, you will see that that is not the case, because let us just apply VGS a little bit positive. Okay, so VGS equal to 0 we have considered. Now I have a battery lying here, case 2. I have a battery lying here, VGS, and I made it positive, exactly like the enhancement mode. Okay, this circuit looks quite similar to enhancement mode's biasing. I have made the gate terminal positive and the source terminal negative, and VGS is now positive. Okay, so VGS is positive. What is going to happen here? So let us just think about it. Let us just think physically about it. What is going to happen? So gate terminal is positively biased now. So positively biased means it will try to pull more and more electrons, which are minority carriers. Though electrons are minority, same thing that happened in case of enhancement MOSFET, right? So electrons are minority carriers, but they are here in this p-type substrate. So these electrons are going to get attracted towards this n channel because of this positive terminal of the battery. Now here you have that oxide layer, so it cannot flow, but the electrons will get attracted and they will crowd this n channel. Okay, more and more electrons will rush through the n channel, and they will gather on top of the n channel. And at the same time, the holes are going to get repelled for the same reason. For the same battery, the holes are going to get repelled. So what will happen? Effectively, the population of the electrons in the channel is going to increase, right? So more and more electrons are going to crowd the entire length of the channel, moving from the substrate towards the n channel. So that means the current will increase. The current is going to increase. So this phenomena that we are seeing here is something new from what we have seen in case of JFETs, right? Because here the behavior that we are seeing is quite similar to what we saw in case of enhancement MOSFET. There was no channel to begin with, but the electrons came and caused the current to
flow. Here we already have a channel, but that does not stop that same phenomena to occur, right? So electrons will again go and the channel will get enhanced, the current will get enhanced, and more current will flow. But on the other hand, VDS is increasing, and that is also going to cause the depletion regions and the pinch off, right? So what kind of a graph do you expect for positive values of VGS? So VGS equal to 0, we already drew. For positive values of VGS, whatever the current we had in case of a certain value of VDS, the current would be more because of these excess electrons going into the N channel. But the phenomena of pinch off is obviously going to occur because VDS alone is sufficient to cause that phenomena to occur. So what kind of a graph do I expect? I expect this set of graphs where I have positive values of VGS. So you can see VGS equal to plus 0.5, plus 1, plus 1.5, all the positive values, right? So the positive values of VGS, this battery signifies this VGS value. You have more current than what we had in case of VGS equal to 0 volt. The pinch off occurs, and that occurs because of this other source VDS and the depletion region forming and choking the channel. That part is same, so the pinch off is occurring, saturation is occurring, but where it is occurring? For current values which is higher than what we had in case of VGS equal to 0 volt. That is the most interesting part and difference, striking difference that we had in case of JFETs. In case of JFETs, VGS equal to 0 was the maximum current that we could have. But now you can have higher values of current as well because the system is operating as if in an enhancement mode. Okay, so this part, it is the operation of this system is entirely similar to what we saw in case of enhancement type MOSFETs. Okay. The other side of the story, VGS equal to VGS less than 0 is known to you because that is very much similar to JFETs again. So let us go and discuss the other side. So VGS negative. So now what I did? Now I attached a battery but in reverse polarity. See, here I have a battery attached which is my VGS, but this time it is less than 0. Case 3 where VGS is less than 0 and the gate terminal is attached to the negative side of the battery. Okay, VGS less than 0. So what is going to happen? The gate terminal is negative now. That means it will attract the holes instead of the electrons. So just consider physically what is going to happen. Here I have a negative potential. So this substrate is full of holes, right? This is a p-type substrate. Majorities are holes. So these holes will get attracted to this negative side of the battery. They again cannot flow because of the oxide layer sitting here, but they can rush into the channel and they can gather inside the channel, right? But inside channel, what do we have? Excess electrons, because that is an N channel, N channel, right? That is an N-type material. So as soon as the holes rush into the channel, what is supposed to happen? The electrons are supposed to meet the holes and recombination is supposed to happen. So as soon as a hole meets an electron, the electrons and hole meet and there is nothing, right? That is recombination. So they just vanish into each other. So that means what? That means as soon as these electrons meet with these holes, their numbers fall down. Their numbers fall down drastically inside the channel. So the amount of available electrons which are responsible for the current to form, number of those electrons start falling drastically as soon as you apply VGS is equal to some negative value. As soon as you apply a negative potential between gate to source due to this attraction to the holes, the N channel loses its electrons due to the phenomena of recombination. Is this clear? Do you understand this? Is it clear?
Yes, ma'am.
Yes.
Okay. Okay. So that means I am losing my electrons inside the channel. That means the number of carriers are falling. That means the current flowing in the system should also fall. Okay. On the other side, VDS is doing its job. VDS is trying to increase the current, but at the same time is also increasing the depletion region. So at one point, the pinch off is going to occur. So before pinch off, the current values that I will be having must be something which is less than what I had in case of VGS equal to 0, because I lost some electrons, at least some electrons I lost to the phenomena of this recombination. So if I want to draw the output characteristics, the graphs that I will get will be below the VGS equal to 0 volt graph. So this was my VGS equal to 0 volt graph. Now I will start getting graphs below this curve because the amount of current flowing will be less because I lost some electrons due to recombination. But still some current would flow and it will again saturate at a certain value of pinch off that is caused by VDS, that is trying to pull the electrons, but in that course it is also increasing the depletion region. Okay, so this way the current will go down and down, and at a certain value the entire channel will be lost of any electrons because all the electrons will be recombined with some holes, no electrons there to carry the electricity anymore, and there you will have VGS off. Okay, so that is the cutoff voltage, that is the negative voltage, maximum negative voltage that you can apply. At that value the current will be completely cut down. Okay, so here let us take a more closer look at the output characteristics that we have drawn. So this is IDSS, the one I am pointing here. This is IDSS. IDSS was my VGS equal to 0 graph. So we saw two different way of operation, two different modes of operation of this device in the values for positive and negative VGS. VGS equal to positive, this entire region is called enhancement mode, while VGS equal to negative is called a depletion mode. So here the formation of depletion region and the phenomena quite similar to JFET operation controls the working in this region. Okay, while in the rest of it, in this region I have enhancement mode of operation, and there gathering more and more electrons into the channel controls the operating principle of this device. So for this reason, this kind of MOSFETs are also sometimes called DE MOSFETs, depletion enhancement type MOSFETs, or simply depletion mode MOSFETs, D MOSFETs. Okay, because they can function in both ways. So you can understand now that if I want to draw the output, I have already drawn the output characteristics. If I want to draw the transfer characteristics, that is also going to look quite similar to JFET, but also a little bit different, because the curves below the 0 volt should look like the JFET behavior only, but I will have some extra values for curves this higher on the positive side of VGS. So let us see this special kind of transfer characteristics. So in transfer characteristics, you draw this, extend this to the other side. Now here, remember, my values of VGS could be negative as well as positive. So the graph spans both first and second quadrant. Okay, so here I have VGS equal to 0. This is my VGS axis, transfer characteristics. X-axis is VGS, Y-axis is ID. So VGS equal to 0, I had a certain amount of current flowing in the circuit, that is IDSS. And that current falls down and becomes 0 at VGS equal to off. So after that you have cut off. But this is quite, this part is quite similar to JFET, isn't it? It's quite similar to JFET. But on the positive side also you have this curve due to this enhancement mode of operation. Okay. So this is in total the depletion type MOSFET and how it works. So yeah, is there any question? Okay, so try to explore this, read it once and try to draw the output and transfer characteristics for these devices that we have not discussed yet, right? So P channel E type MOSFET and P channel D type MOSFET, I'm sure you will be able to draw the characteristics graphs for these devices as well, and try to look into the quadrants as well. That is the most fundamental part of understanding how these devices function, because you have to understand that until and unless we discuss only N channel type MOSFET, the current flow direction will be same, right? So current flows always from drain to source because the carriers flow from source to drain. But if I can, please. So in case of P channel MOSFET, the flow of current will be on the other direction, and try to figure out the graphs for those devices as well, because your ID, you need to consider that as negative. Okay, so you are expected to have graphs like this. I am just giving you a glimpse, but try to figure it out, try to draw them on your own. N channel, P channel, depletion type, enhancement type, and output characteristics, transfer characteristics. In total, you have 8 graphs. Try to draw them one by one and try to understand, grow your understanding of these devices. Okay, so I will stop at this point today, and I want you to go and thoroughly read about MOSFETs and try to draw all these curves, try to reproduce all these curves on your own. Okay, so I will stop here. If you have any questions, you can ask.